Okay, you're welcome to another session of Ugbs 202, Business Mathematics. Today we want to look at decision trees, another form of probabilities. It adopts the same concept of probability distributions, but this time around we're going to do it graphically. Basically, decision trees are more like it shows a graphical representation of the sequence within which certain events would occur or certain business decisions are made. Okay, so normally we use it to evaluate possible alternatives of events, right, of any event. And so, but just that here, we're going to represent the events as they occur in some diagram using certain things we call nodes and arcs, or basically like some squares or circles and then and some arrows, right? So we'll go through some basic conventions of decision trees or certain facts that we need to know about decision trees, and then we'll apply them, solve a certain question, and we should all be fine. In fact, this is a very basic concept that I presume we are going to enjoy so much. Now, we're saying that in a decision tree, there exist square nodes and circle nodes, where a square node represents a decision point or time, and then a circle node represents uncertain events with possible outcomes. What this is saying is, in the course of we're doing our representations in a graph or in the diagram, certain times we would represent certain events with circles, and other times we would also represent certain events with squares. Where you would have to represent an event with a square, it means that at that point, the firm or the business has to make a decision or is about making a decision. For instance, say, consider the case of whether we produce or not to produce, whether we buy or we do not buy. At that point, we have to make a decision. Now, how about the second instance is where we would have to represent an event with a circle or a circular node. Now, when an instance like that occurs, what it means is that at that point, the event is only evaluating possible outcomes, right? We're only going to evaluate the possible outcomes. And so, for instance, you could take a typical example as, say, if a business launches a new product, the product could be successful or unsuccessful. It could be a success or a failure, we could make profits or not make profits. Now, in that instance, there are possible outcomes. The firm doesn't have control over it and it's not making a decision, but it's only going to evaluate the possible options. What would I get if it turns out that the launch was successful? Or what would be the scenario if it turns out to be unsuccessful? So in that case, we are only evaluating the possible outcomes. Now, another case, there exist branches where a branch coming out from a square node is an alternative, where the branch coming out of the circle node is a possible outcome of an uncertain event. Okay, so normally the branches we use arrows, right? And so when we use a square node, it means at that point we are actually making a decision. And so the direction of that arrow determines what decision we have made at that point. And the same, but for the case of circular nodes or circle node, well, at that point we are only actually evaluating our possible outcomes or our chances there. And so, well, the arrow just tells us, well, this is the outcome of the two or more or whatever outcomes there is at that point. Now, each branch coming out of a circle has an assigned probability. The sum of the probabilities of all branches out of the particular circular node must be 1. Okay, so just like we saw early on in the previous slides that every or all probabilities sum up to 1, the same idea is being captured here. Now, if we have a certain circular node and there are a number of options we are evaluating there, then the probabilities attached to all the possible outcomes there in total must add up to 1. Okay, Now, it says that monetary values or profit or revenue earned after making a particular decision or choosing an alternative are placed on the end of the branch coming out of a node. Well, all we are saying is this is just describing how we do the representation in the diagram. While whatever the information there, we normally would write it on the arrow. I'll show you a pictorial or a diagram of a typical decision tree, and we'll see how that works out. So I'll touch on that point when you see the diagram. Okay, so it says costs incurred on making a particular decision are typically placed on the branch coming out of it, the same instance. Okay, and then decision at any point in time is based on the expected monetary value. Now, the expected monetary value is just the same idea as we saw when we were doing the probability distributions, as in when we were finding the mean or the expected value, where we multiply each probability by the respective random variable. So it's the same idea here. Well, we'll see it from the diagram. So consider a diagram as this. So this is how a decision tree looks like. You're given a business problem, and then we rewrite or represent that business problem in this form or using this diagram. And these nodes, you can see the square nodes here. You see the circle nodes also here, right? Now, the square nodes are always when, or are used always when we have to make a decision, right? When we have to make a decision. Now, consider this one. So let's take the case of, say, a firm decided on whether to bid for a contract or not to bid. Now, if you read that problem, I am deciding whether to bid or not to bid. That is a decision that has to be made. And so here, that decision or that event must be represented using a square node. And so here you have this and you have that. We do not bid here, or we bid. Same applies for an instance here. Now look at these ones here, the circular nodes. For the circular nodes, we say here what we do is to evaluate our outcomes or possible alternatives. And so for every circular node or for every circle node, there must be some probabilities represented on the arrows, as well as whatever monetary returns, whether it's revenue or cost, also attached to that arrow. So here in this case, for instance, the probability is here, what the event is stated here, and then the monetary event, 15K here representing 15,000, and 0.7 here going in that order, right? So basically, this is how the decision tree looks like. But the only thing is how you are able to read and understand what the business problem is when you are supposed to use a square node and when you are supposed to use what? A circle node. That is just the basic thing with decision trees. Okay, so here we say that decision trees at any point in time is based on the expected value, expected monetary value approach. And so if you look at the instance here, for instance here, what we'll do is, if you want to find the expected monetary value for this event here, given this case, you take this probability, multiply it by whatever the monetary value there is here, and the same applies to this. So take this instance, this times this plus this times that will give us the expected monetary value of this event. That's what that point is saying. Now, it says that the solution to the entire problem is based on a so-called approach called the folding back process. Now, think about it. This is a tree. Now, in trying to evaluate this to decide on the final decision to make or the main, to solve that main problem, we would have to chop all these branches or kind of fold them back gradually until we arrive at the final decision at point 1. And so the folding back period is done from right to left, or from the highest node to the least node. And so here, for instance, if I'm supposed to do the folding back process, I start from node 8. This is a circle node where all I have to do is evaluate or find the expected monetary value. So what I do here is I take the probability, multiply it by the monetary value here, plus this probability multiplied by this. Whatever it is, I put the value here. So I am done with this one here. I do the same for this. I do the same for this. I come here. Whatever the value here is, or from this computation, will be the value at this point here. And so I do the same, and I do that. If you notice that I take this one, I fold it onto this, I take this one, I fold it, and it goes on and on and on until I get to the final node here. When you get to a decision node where we have to make a choice, or we have to actually make a decision, you evaluate the options that are available. So whatever the monetary value there is here, and this value, consider, in this case we have 3, consider the one with the highest possible value, and then pick it. That becomes your decision. Then at this point as well, you compare it to whatever is here, and then you make your final decision. Very basic concept, very simple concept. So let's try and take an example, and then we'll see how it turns out to be. Okay, so let's take a few seconds and read through the question, and then we'll see how it works out. Okay, so a software company has just won a contract worth $80 million if it delivers a successful product on time, but only $40 million if it is late. It faces a problem now of whether to produce the work in-house, that is by itself, or to subcontract. To subcontract, the work would cost $50 million. But the local contractor is so fast and reliable as to make it certain that the successful software is produced on time. If the work is produced by itself, the cost would only be $20 million. But based on past experience, it would only have a 90% chance of being successful. In the event of the software not being successful, there would be insufficient time to rewrite the whole package internally. But there would be an option of either a late rejection of the contract at a further cost of $10 million, or a late subcontracting of the work on the same terms as before. With this late start, the local contractor is estimated to have only a 50-50 chance of producing it late. In this case, the contractor still has to be paid $50 million regardless of whether he meets the deadline or not. So here, the A portion says draw a decision tree for the software company and then calculate the expected values as approximates and recommend a course of action to the software company with reasons. Okay, so this is our problem here. And so what I advise you do is, well, first take some minutes, read the question or read the problem, try and understand what the problem requires of you, and then identify the main problem. The main problem is, what major decision does this question require you to make? Because that is what is going to determine what advice you're going to give to the company, or it would determine the course of action you're going to recommend at the end of the day. So think about it here. Now, this is a company which says that he has just won a contract of $80 million. That is if it delivers a successful product on time, but only $40 million if it is late. So if the contract is delivered on time, it would and is successful, it will make $80 million. But if it's not on time, you're going to get half of the amount, because you're going to pay penalty for the late delivery. So the main decision here, it says that it faces a problem now of whether to produce the work in-house, that is by itself, or to subcontract. So here, if we are going to start drawing our decision tree, the first node we are going to draw would be a square node. Now, why? Because at that point, that is where we want to make a decision. And so take it, most of the time, or let's say 100% of the time, your first node is always a decision node. Now, that is the major decision you want to take. And so here, the first thing I'll do is, okay, so let's go through the question together and see how we work our way around it. Okay, so like I was saying, the major problem here is to whether to decide to subcontract it or to produce it themselves. So my first node would be to have node 1, right? And what I do is I have an arrow coming out and another one, because there are two options, right? So what I do is I can just write itself. Well, for labeling them, just write it as you understand, right? And just make sure you pick some cues from what the question is saying. And then here, I write subcontract. So I'm done representing the first instance. Okay, so the next thing to do is I read another sentence and see whether I would be able to get some information that I can pen down in my diagram. Now, there's one thing I want you to always have at the back of your mind. You do not have any statement in the question or in the problem just being there for no reason. Every statement will have something to do with these diagrams. That's why I entreat you to read it one after the other carefully so that you don't miss out anything. Okay, so we've been able to say that it faces the problem now of whether to produce the work in-house or to subcontract. So now let's go ahead and see. It says that to subcontract, the work would cost 50 million. But the local contractor is so fast and reliable as to make it certain the successful software is produced on time. Okay, so, well, think about it. If we subcontract, it would cost us 50 million. This is how we represent cost. For cost, you write it inside. So 50 million, let's say it is cedis or dollars or whichever. So in our case, it was dollars. So 50 million. So I put minus 50, indicating it's a cost. Now look at the continuation of this sentence. It says that, but the local contractor is so fast and reliable as to make it certain the successful software is produced on time. So the contractor is so reliable. It means that for him, once you give him the contract, he will give you the work on time. And what does the question say? When we produce whatever the software on time, it says that if we produce the software on time, we will gain 80 million if it delivers a successful product on time. So here, the monetary value we're going to get here will be what? 80 million. So you see, we've been able to put down the first paragraph successfully in our diagram. So let's move on to the next diagram. Okay, now if the work is produced by itself, so this time around we are going to move along at the second direction. This is subcontract. This is producing itself. So here, so you must now know that we are going to move on to this dimension. So anything you're going to represent should be coming from this arc. Okay, so it says if the work is produced by itself, it will cost only 20 million. Okay, so if we produce it by ourselves, it will cost us only 20 million. Okay, now let's go ahead. But based on past experience, it will have only 90% chance of being successful. It will have only 90% chance of being successful. Think about it. Now, is that a decision or some outcome, possible outcomes. It's an outcome. Now, if we produce it in-house, it is possible we could be successful in producing it, or we may not be successful. Okay, so here we will introduce a circle node, and I'll label it node 2. And then here it could be success or unsuccessful. Okay, so this is unsuccessful in case you're not seeing it too clearly, and this is successful. Now, the question said, or the statement said, from or based on past experience, it would only have 90% chance of being successful. So we have a 0.9% chance of being successful. You do know that from the complement rule in probabilities, all probabilities must add up to 1. And so here, if we have a 90% chance of being successful, then what is the chance of we failing? It's going to be 0.1. Remember, from the information we gave you, we said that the probabilities of all the possible outcomes must add up to 1. And so if you drew just this 0.9, this is not adding up to 1. But if I add the complement of this, then this becomes 0.9 plus 0.1 will now add up to 1. So we've been able to do that successfully. Okay. Now, let's put in the other portions of the information. Now, if we produce it successfully, what happens? Now, it means we are going to get the 80 million, isn't it? That is on time. But if we do not produce it successfully, then it is possible something will happen. But let's go ahead and see what the information says. Now, in the event of the software not being successful, so here, if the software is not successful, see, so we are going to move along this line now here. In the event the software not being successful, there would be insufficient time to rewrite the whole package internally. But there would be an option of either a late rejection of the contract at a further cost of 10 million or a late subcontracting of the work on the same terms as before. So think about it. Now, supposing we are unsuccessful, we could decide to stay unsuccessful and not get anything, or probably we could quickly go and solicit the services of the local contractor and ask him to do the thing for us. And remember, the local contractor, they said, is so certain that he would give you the work successfully. So would that be a chance that we have to evaluate, or it's a decision we have to make? To me, I guess it's a decision. Let's see it. So here, it's going to be a decision. So here, I'll label it 3. And the decision here would be either we take the late submission or we subcontract. Okay, so here, now, if we take a late rejection, it means we want to face a late rejection. It means that, well, we didn't get it successful the first time, so we try to redo it again so that we would have to probably, we will not meet the deadline. So here, the late submission, the late rejection would come at a further cost. It means we'll have to buy some new materials and redo it. So we would incur some further cost of 10 million. Or we could decide to subcontract it to the local contractor on the same terms as before. If you're subcontracting to the subcontractor, what do? He said it will cost us 50 million. Here, that is what we've done. Okay, now let's continue and finish it quickly. We are almost there. Or a late subcontracting on the same terms as before. Now, with the late start, the subcontractor is estimated to have only a 50-50 chance of producing it late. Okay, so if we subcontract, there is the chance that the subcontractor could produce it on time or could be late. And so if it's a chance, then it becomes this, a circle node. So here we could be late and then on time. And it's a 50-50 chance, so 0.5, 0.5. Okay, the product will lead. Then in this case, the subcontractor has to be paid 50 million regardless of whether he meets the deadline or not. So here we have been able to represent whatever information we have here. Now think about it. So let's just, at the end of every node, you need to have some monetary values there for you to evaluate, right? Now, if we have, come back to the top, it says that if we produce it on time, we'll get 80 million. If we actually did not do it on time, we'll only earn 40 million. So for a late submission, we will get 40 million. For every late submission or possible outcome of late submission, we'll get 40 million. For an early submission, you're going to have what? 80 million. We are done. That's our decision tree. We've been able to represent. And so if you consider every information we've put on our diagram here, so look at it carefully from the beginning. So here, when we have producing it itself way down to the final portion, you do see that we have every information here. So the next thing we'll do is just to do our folding back period, our folding back. And so you start from the last node to the first one. So here from node 1, so you start from node 4, you just name it node 4. For node 4, it's we're only evaluating the chance, so we'll call it a chance node. So what we do here is our 0.5 times 40 plus 0.5 times 80. What we have here is 20 plus 40, we have 60. So I put my 60 here, right? So now the next one to do is to evaluate node 3. Okay, I hope you're following. Now for node 3 here is a decision node. We have to make a decision, right? So here, from this point, if it's a late submission, we will earn 40 million. Now, but we must incur a cost of what? 10 million. So what we have here will be 30 million. Here we evaluated this and we have 60 million. So we are subcontracting and we'll incur a cost of 50 million. And so here, the monetary value would be 10 because 60 minus 50, the cost will be 10. Now, you now have 30 here, you have 10 here. The decision is to choose one. So what do you think? I think we always prefer more to less. So you choose 30. So you see, then it continues in that order. You multiply 0.1 times 30 plus 0.9 times 80. Whatever that value they put it here. Find the difference between this. Find the difference between... Okay, so here, this is what I'm saying. So here, I have 30 here. 30 times 0.1 plus 0.9 times 8. I sum them. I put the value here. Then I'm done with node 2. I want to come to node 1. For node 1, I have a cost of 20 million here. Whatever the value here, I find the difference. And then here is 80 million. I find the difference. Then I compare the two. The one that has the value, I put the value here, and that becomes the decision. So in this case, whatever gives me the highest revenue or the route that I get the highest returns determines what my final decision will be. And that is how we deal with all decision tree problems. Okay, so I hope that was fairly easy. But all you need to do is to practice, 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 practice. Trust me, decision tree problems do not come any different from what we have seen. Well, the only difference would be that the problem may be more composed and there will be a lot more than this one. This one seemed quite short. It's quite a brief problem. But you could have other problems that are quite bulky. But the approach is the same. Read every sentence. There is something between the first full stop and then the next full stop, or the commas. You just put them together, draw your diagram successfully, go over again and make sure that you've represented every information that needs to be there. Do your folding back, and then you're done. All right, thank you. I hope you enjoyed this session. I'll see you in the next session.